Hello, Nick Marotta.
Nick Marotta is here. So, for the benefit of somebody who's watching us for the very, very first time today, for over 10 weeks now, Steve Bjork, and if you're not familiar with Steve Bjork, he's that guy who made Audio Spectrum Analyzer, right? So,
amongst other things.
So Steve Bjork has been taking us through how to talk to the 6809 6809 processor, teaching us the registers and some of the language and commands, and building a nice, wonderful foundation for us to understand that CPU. Today, we're going to take it beyond the theory, and we're going to jump into practical application. We're going to be looking at, source code and assembling things and looking at things. And John Lowry is here. Yo, Stevie Stroh. Yo. What's going on with you there, John Lowry? So are we ready to jump in, Mr. Bjork, and start talking about segment 11, session 11 here in our ongoing series?
I think we're about pretty much ready to go here. Just a word of warning. I'm actually going to have in the slides the entire assembly language for this simple demo of a bouncing ball on the screen. And actually, before we actually start that, is there a way you could bring that up for people to see, Stevie?
Do you want to see it in the slide, or you want to see it in Notepad++? I've got it open up in both, actually.
Oh, no. I actually want to see the executable.
Oh, the executable itself.
What it's going to do, so they get an idea.
Yes. Bear with me 1 second here, and let me just hit up arrow and repeat my last command. So assemb space dot move VCC. All right. Let's get it up on the screen. Let's get VCC going. Let me, of course, I'm not sure if I go to full left screen here. And by the way, the fact that I was able to do this quickly is thank you to Paul Fiscarelli setting up his Long Branch Never environment for us, where we can now run editor. So it's bouncing. I don't know how well you can see it because VCC is running small. What is a way to get VCC to run full screen? I don't even know. Isn't there a way to make VCC bigger?
Isn't there like a 2x zoom or something?
I don't know.
Yeah, you have to go to config.
Yeah, display.
And then display, and then
frame skip. Yeah. Composite, scan lines, F8 throttle, allow resize. There we go.
That's it.
We're going to hit allow resize. So now if I maximize, okay, so the aspect ratio is distorted. However, we can see now by me maximizing this that what we have on the screen here is a bouncing ball or dot or pair of pixels, whatever you want to call it here.
See, folks, this is my version of Hello World. It's got to be graphic related. This is a very simple basic program. It's only about 160 bytes in size. And that includes the initialization that you need to do for the Coco to display a P mode 4 screen, clear it, and then actually move the dot around on the screen.
And set the color.
Mm-hmm.
There we go.
All right. Well, why don't we stop that, and you got the slide there. Little off the screen, though.
Actually, I think I'm all the way at the bottom of the slides. That's why.
Okay. All right. It's my monitor. Sorry.
Okay. Let me get to the top of the slide, and yes.
Okay. And I'm going to bring up my copy myself here so I can follow along too. Make sure I get everything right here. But basically, what we're going to do is basically go through this program, which has some information that you need to set up so that the program knows about the color computer. See, that's one thing about BASIC when you program it. It knows about the machine it runs on. So it does a lot of the setups. It understands what P mode 4 is and how to set the screen. Well, in assembly, it don't know any of that stuff. So we have to do some definitions at the beginning of the program to tell it about the Coco. Then we've got to tell it more about the way the program is. And another thing I wanted to bring up too is that we don't have things like variable A or B or C that we can store information. You have to create your own variables in assembly language, and part of the initial part of the program goes through and sets that up. So one thing too that I did is in this demo for this program, it's all fully commented. Not guaranteeing the spelling of everything, but it's all fully commented. But why don't we go ahead and go to the next slide? We're going to spend a little time on this one so people have a chance to figure out where they can download today's lesson. There's 2 files that's in lesson11.zip. One is the entire source code for the program, and another one is the diskette image for VCC.
Okay, and I will say this audibly right now for the benefit of somebody listening to this later on a podcast. We'll also put this in the description later on, but it's haunthackers.com/data/lesson11zip, all lowercase.
Now,
URL.
I have a website that we're going to use later for all these lessons. This lesson will also go through. It'll be coco4.com. That will happen sometime next week. Right now, I've got to move it to another server that's got proper security certificates and like that, because good old Mozilla Firefox likes to complain if you don't have everything properly set up with the security certificates. So anyways, but haunthackers.com, it does work. You can download it from that location. And we'll also be making this slide available later. Right now, Stevie and I are working on taking the first 10 lessons and making videos and the slides available for you. And this won't be the second half of stuff. Anyways, let's go to the next slide. All right. We're going to be using the P-Mode screen, P-Mode 4 screen, which is basically 256 dots across by 192 scan lines. And I kind of say 256 dots across with a certain caveat. If you put just a single dot on this screen and you're using a NTSC system like they have here in the US, that dot may be red or blue, not white. So one of the things I'll be doing is actually making the dot that moves around the screen 2 dots wide, because then it'll actually come out as white. And that's because of the artifacting in the mode like that. So that's part. Initially, we're going to have a dot, which is actually physically 2 dots wide for our ball moving around on the screen. Let's go to the next slide. Since, let's see, since we're doing it as 2 dots wide, there's technically only 128 positions going across the screen.
And that's to keep it white no matter what position you put it in.
Exactly. So, and the way this particular mode works is that every single byte of screen memory contains 4 dots. And what they do is they use 2 bits together. Whether this would happen to be a P-Mode screen, which is P-Mode 3, that's the one that has that beautiful green, yellow. I don't even use that mode anymore, so I can't remember.
Blue and red.
Blue and red, yeah.
And then, or the alternate color set, which is even worse, which is the what do they call it? Buff, cyan, magenta, and orange.
Yeah, it's just, yeah. That's the reason why when I was doing this stuff all the time, I was using this P-Mode 4 screen just to make sure that things didn't, well, let's put it, black, white, red, blue is much more colors, better colors for especially space games. So, but anyways, on this particular mode, we're trying to make sure that when it comes to putting the dot on there, we want 2 dots next to each other so it doesn't shift in color as it goes across the screen. And this little pattern that you see here on the 3rd line is the binary pattern showing the bits of the byte. And you can see the first, you have 1 1 followed by 6 zeros. That would be the dot on the most left-hand side of that byte. In other words, if it was the first byte on the screen and you want it to be the first dot, you would use that first pattern. Then if you move it over 1, you would use the second pattern where it's a couple of zeros, a couple of 1s, followed by 4 zeros. That physically moves the dot over 1 more. Same thing for the last 2. It's moving the dot more and more. Once you get past that 4th location, that byte, Then it goes to the next byte and starts over again at the beginning. So that's how the graphics memory works, is the highest bits are the most left side of the dots in that byte, and etc. Now, if you were doing it strictly as one dot per dot, I mean 1 bit per dot, you would have just using it would be like 1 followed by 7 zeros and like that. Now, if you're doing 16 color mode, like on the Coco 3, you would use the top half, or 4 bits, to represent 1 dot, and the next 4 bits would represent the other dot. So you only have 2 dots per byte.
Yeah, and if I could just take a moment here to say this might help if anybody was still trying to chew on binary and not quite getting where the bits fall into it. And I think, Curtis, you had mentioned this in the past too, but moving a bit around seems to make a lot of sense on the P mode 4 screen because it's 1 bit per pixel. So in this case here, we're looking at 1 byte, which is 8 bits. And everywhere you see a 1, this is a pixel that is turned on. Remember, binary is on or off. So we see 2 solid pixels followed by 6 empty dots, and then it shifts over 2 pixels. So now we can see that we've got 2 pixels. We got 2 leading zeros. We got 2 pixels. So the ball just moved 2 pixels to the right. Now it's moved 4 pixels to the right. Now it's moved 6 pixels to the right. So you can, in a way here, even though we're still looking at zeros and ones on a slide, you can kind of see where it's a little bit more visual now. There's 2 pixels kind of panning through these 8. So if you
can actually poke these on the screen to take a look at if you want to see it even from basic. Just
right.
Sit down and get a visual cue as to what you're doing.
Yeah. So
exactly.
And so hopefully this will make even more sense when we start looking at the demo. Again, I love this here too. John Lowry says there are 2 types of people in the world: those who understand binary and those who don't. And of course, that's written in binary, right? So
exactly.
I love that joke.
The main thing I'm trying to say here is this is generally how graphics work on the Coco. Is the bits are stored in the bytes, and it pulls that information out and then plays it out as the dots on the screen.
And this is actually called bit plane mode, if I remember correctly. Correct?
Yeah, exactly. Bit plane or bit mode graphics. Now, as we said, we've got 128 positions going across the screen. We divide that by 4 since we have 4 dots per byte. It means that it takes 32 bytes to do 1 scan line worth of information. And then if you have 192 scan lines, that makes a total of 6,144 bytes to represent the screen. That's getting to be a bit of information to push around.
Yeah.
Yeah. Let's as Steve's already done, we're moved on to the next slide, and we're actually talking about the source code. This is part of the source code that I'm giving you, and it's done up in segments. The first segment here is defining information about the color computer. So the program knows what's going on. Now, you could actually just put this information directly in as the numbers in your program. I like to put it at the beginning of the program so that it makes it easier to understand what's going on and change. And some of this information we're going to be talking about is when you want to set up a graphics mode, you have to set things up in the SAM chip. That's the synchronous address multiplexer chip. And this is the thing that handles where video RAM is, what video mode you're in, does refresh, does a lot of things on the computer. It's one of the reasons why we can use less expensive dynamic memory on the Coco instead of static back in the day. But anyways, you need to be able to tell the system how to set up for this P mode 4 that we're going to do. And this information that you see here, without going into a lot of detail, everybody's going to be able to look at it later and figure out it has the information for setting up the SAM. All those labels, which are the thing that you see on the far left-hand side, that's a label or symbol for information that you're going to use later. And
would that be similar to a variable in a sense?
This is more of it's more of a constant, but it can be considered a variable. But we'll use variable for that term for right now.
Okay.
You will notice something that I've used upper and lower case. Believe it or not, the assembler is sensitive to that. So if you type in a label or symbol that the case doesn't match, it's like a totally different one. If I had used lowercase for Sam, and then somewhere else I used uppercase for Sam on these guys, they would be seen as totally separate variables. In other words, an uppercase S is not the same as a lowercase s. They see it as different letters. So that's something you have to watch out for. Is if you use uppercase, watch out for it.
They're definitely case sensitive.
Yeah, definitely case. Now, one of the things I did here to make life easier for myself is stuff that talks to the Sam. I capitalized the 3 letters of Sam because I wanted that to stand out. The other letters that you see there, VReg, for example, is talking about Sam's video mode registers. And I try to make the symbol somewhat
self-explanatory.
Self-explanatory, exactly.
Being that SAM is an acronym, it would make sense to have it as capitals.
Yep. And the last 2 lines down at the bottom have to do with setting up the video display port, which is FF22 on the Coco. This is one the PIA is on there and puts out information to the video display generator. That also needs to be set up. So that's what those last 2 lines are doing. They're what port you're going to have to put information out to. And guess what? The next line is the information you're going to put on that stupid port. So...
And I will mention here too, I mean, you can write a semi-language where you're changing the values in these memory locations directly, like directly doing a story at FFC0 or whatever to set up your SAM, your VDG, etc. But if you try to look at the code, 6 months later, or if somebody else is trying to look at the code, they have to try to look up in a table or chart somewhere. What does that memory address do? I can't remember type thing. So having your labels set up like this, so it's much more self-explanatory, it really helps you debug your code.
By the way, the comments that you see on the left-hand side do not affect your program. Be verbose. Label more than you think, because at some point you're going to come back and look at your code and it's going to say, what the F? You need these comments to explain to you. So while you're writing the program, if you need to put down 2 or 3 lines to explain what that one line of code is doing, do it.
Yes.
It just makes life easier for you later.
I can totally vouch for that after going through NitroSign code I wrote 25 years ago.
Mm-hmm. Okay, let's go ahead and pop to the next slide. All right, this is more definitions. We're going to define information about the screen, the graphic screen that we're going to be doing stuff to. The max dots of X and Y, that's the size of the screen. We've got the number of bytes per line. Yes, I could put the number 32 in the program, but this just makes it much easier. Also, there's different modes on the Coco that have different number of bytes per scan line, especially in the Coco 3. And there's a typo there. It didn't get the Y when I typed in bytes. Oh well, in the documentation.
Yeah, in the comment, I see that.
Yeah. Okay. And then it's got a location for where screen memory is at, the size of the screen. And this last one's going to be used much later in the program. This has helped me to understand how many CPU clock cycles there are in a 60th of a second. Just something I'm going to use later in the program. Easier to put it up at the beginning to define it. See, if I was running at double speed, I would want to change that number.
Mm-hmm.
Okay. Yeah. See, it makes it easier to modify your code because you change it in one spot and it affects the rest of the program.
Yeah, every reference to that label later on will use whatever changed value you do up at the top here, so you don't have to remember to change 15 different lines later on in a large program that all had that same value being used.
And by the way, if you were working on, say, a PAL system, you would probably want to change that too. So because they clock at a different frequency.
Yeah, 50 hertz.
Yep. Anyways, remember before I said there's no such thing as like variables like the letter A and letter B, and you have to kind of define your own variables. Well, that's what we're going to do here, is we're going to define some variables for us to store information in. And this goes in the direct page or page 0. So I simply do a org 0 to tell the assembler, hey, the stuff that I'm mentioning here, it starts at the beginning of memory. And the first thing is this screen. This is a variable for me to let me know where where my screen is that I'm currently working on. And this will become a very important variable later when we do screen flipping.
This is a 16 bot address?
This is a 16 bot. The RMB means
I'm just messing. I'm messing with your typo here. That's all.
Okay.
16 bot address.
Oh, okay, yeah. See, you can put whatever you want in the comments.
You did. Hey, you did mention that. Don't blame me for spelling at the beginning of the sentence.
Yeah. I was typing this stuff in pretty fast. And one thing about editors, they do not have a spell check.
Yes, that's true. It's on Notepad++, right? So.
Yeah.
So.
If I ever write an editor, I'm putting a spell check in it.
Put at least 16 bots in that too while you're at it. So.
Okay. Anyway, so this is a 16-bit address that contains where our screen is in memory that we're working on. Because if we're doing page flipping, you would actually have two different screens, and you got to be able to tell the program what screen you're working on. So I'm setting that up. Dot memory. This is where we drew the ball last time. And then what was there, we're going to use that to store the graphics data that was at a location. Because when we draw our ball on the screen, I want to be able to erase it. So what I want to remember is where that ball was in that screen memory and what was there. So before I draw the dot there, I use this information to erase the last time. Remove what was on the screen the last time, so he erases the old ball and draws the new one in its location. And go ahead.
Oh, I was just going to ask: have we explained what RMB means yet?
I don't think I did. I was hoping people have read the documentation for the assembler, but no. RMB means reserved memory byte. And
yeah, so an RMB2 means it's reserving 2 bytes, and where that is getting addressed is based on the org statement, the origin statement. So we've said, we're starting at memory address 0 with the org statement. This screen will now reserve 2 bytes at location 0. Dot memory will reserve the next 2 bytes, so that'll be location 2, etc.
Exactly, and these are in the direct page, which I said in our previous lessons when we talked about memory addressing. Direct page is a shorthand for addressing information in memory. So it allows you to do it much faster, and without the it actually reduces the size of the instructions. So these are variables that will get used. They're important, so I put them in direct page. All right, let's go to the next slide. I'm not going to try and spend too much on these things, but here we go. The following is information about the X and Y position of our dot that's moving on the screen, along with its delta, or another way to look at it is X and Y speed. Now, these are being reserved as 16-bit values, in other words, 2 bytes. And the reason why I'm breaking this up is the most significant byte, which is the first byte, is the whole number or integer number of its position or speed. The second byte is how I'm doing fractional or something. Like, think of it as like there's a decimal point between the first number and second number. The second number is being used for like 0.01 or something like that. It's basically giving a fractional speed, so we can actually have things move, at different speeds, different angles. If it was moving strictly 1 by 1, it would be a very boring bounce around the edges of the screen.
Yeah, just a straight 45-degree angle bounce. And this way you can vary it to whatever angle you want.
And we'll be seeing that when we actually do the initialization, how we play around with it. But it's a very simple way to do real numbers, or real numbers, instead of just doing but you're doing the math as integer math, which is what the microprocessor does very fast. So when we actually get in there and do this stuff, we'll see that how this is used that way. But once again, we're setting up, this is like my variable X, variable Y, and variable XS for speed of X, and YS for the variable speed for Y. It's just a very fast way of doing it. Next slide. In programs, and by the way, the org 3F00, that is setting up in at the end of the first 16K of RAM. And this particular program is less than 256 bytes, so starting where I did, it will fit in there just fine. And yes, I do think in hex. And I can cast spells too. So anyways, this helps us set up some information that we're going to use to draw the particular graphics dot on the screen. And as I said before in our documentation, 2 bits together represent the actual dot on the screen. And you have to do 2 things when you're going to put something up on the screen. And you don't want to destroy the graphics that are around it. You have to mask, because if you were just to write in something where it's 1 1 followed by 6 zeros onto the screen, it would put the white dot up there, but it would then set the other 3 dots after it as black. And if you had graphics up on the screen, you would now start getting a white dot with 3 black dots behind it. You don't want that. You just want to draw the white dot. And this table here does our masking for us. This is what we talk when we're doing graphics. This is what we talk about masking. This is what's going on. So the first byte allows us to figure out which bits we're going to change and which ones we want left alone. And believe it or not, it's the 0 bits that we want to change, and the 1 in our first example, and the 1 bits we don't. And what we're going to do is we're going to AND this to the screen. So we're going to take what's on the screen and this, and it's going to take the dots we want to change and make them 0. Well, that just takes the dots we want to change and make them black. Well, the next byte, we OR to that information, and it makes those dots white again. It looks like a long ways to go around it, but what it does is it forces us only to change the first 2 bits and leave the other bits alone.
Leaving your background graphics
Exactly.
untouched.
The first byte is the mask. The second byte is the actual color that we're putting in there.
Now,
So
Stevie, you actually demonstrated this in one of your basic lessons when you're doing a little spaceship with a see-through window, if I remember correctly. Is there a way that you can think of explaining this for anybody that's new to masking? That might be easy to understand.
Well, so we're talking about doing like the paper cutout of the screen behind it before we put it on there.
Exactly.
And so we're basically cutting out, in this case here, on the first line, these 2 zeros is what we're cutting out. So we're basically saying in this 1 byte, or this 1 group of 8 pixels on the screen, we're going to cut out a hole of just 2 pixels, but we're going to leave the rest of that alone. And in the second pass, we're going to fill in that hole with whatever part of our image that we want to put on there. Yeah. And so because we're dealing with black and white, it's almost irrelevant, but when we're dealing with colors and backgrounds, you have to respect what's there. You have to respect what other bits were already on the screen. So you go in with a mask, think about you're going to put masking tape over before you spray paint, right? So everywhere the tape is not going to get covered. So we're just taping off the screen that we don't want to get painted, right?
Mm-hmm. Okay. Everybody on the panel got that?
I just figured since Stevie's more of a beginner on this, on assembly language, he would probably be able to explain it better than either one of us could.
Yeah. Okay, well, let's go to the next slide. All right. We're going to actually do a subroutine next. This is a routine that I'm going to actually use twice in the program. So subroutines allow us to write the program once and use it many times. This little bit of code. And this one here has to do with setting up the SAM chip. Now, most of the time when you talk and you're setting up information for things that are connected to the computer, you have an address you talk to and you send it data, like store number to it. Not the SAM. The SAM is a very weird thing. You have to sit there and look at even and odd addresses. If it's even, you're clearing the bit. If it's odd, you're setting it. It's just a funky way to do it, but hey.
Yeah, basically they mapped it so that every bit on the SAM requires you to write or read an entire byte.
Yeah, look, it's the fact that you're writing even or odd sets or reset the bits. And that's basically, if you just get from there that you have to write to memory locations that are even or odd to set the information, that's all you need to know. And what I like to do when I do my routine is I like to explain with comments before it what registers you used, how they're used, what's information's going in. what registers will get changed, and if those registers that are passing information in are changed, I like to know about it. So basically, I'm using the registers that are built in the CPU, the A, B, and X registers, to pass information to this routine so it knows what to do. Pretty much straightforward, Steve?
Yeah, sure.
Okay.
Yep. It's the same in BASIC if you reserve some variables for a Go sub, and your Go sub is going to modify A, B, S, B, and whatever. Okay,
the next slide, it goes through, and this is the actual routine. Now, as you recall, the letter A had the data, and we've got to figure out what is the first bit, which is the lowest bit, the bit to the farthest right. So we do a logically shift to the right A, which takes that bit, the lowest bit, bit 0, and puts it into the carry flag. And then we can respond to what the carry flag is. And I tell it to branch if the carry flag is set to somewhere later in the code. And the next thing simply does a store A. It doesn't matter what we're storing there. But by storing A at X, since this point here, the bit was 0, we're storing it at the even address, and then we're telling X to move forward twice. So this is actually setting 0 to the SAM chip. As I said, it's convoluted to do it, but that's what it's doing. If you notice, there's a branch, set SAM data 1. That's where we branched if the bit was set. And that one there moves X forward off the even address to the odd address. Then it stores A at the odd address and move X by 1. And then it's very simply after that, it decrements B, which had the number of bits we have to update at this time, and then branch back up to the top of all this gobbledygook to continue doing bits if we haven't gone through them. That decrement B basically will take B and subtract 1 from it, and the 0 flag gets set or reset based on the status of B. Once B reaches 0, it will be equal to 0 and won't loop anymore. So that's all this routine does, is goes through, counts the number of bits I wanted to set, goes through and figures out what those bits are, and sets SAM accordingly. But you can see why I didn't want to put this twice in my code. I just only wanted to do it once. So I made it as a subroutine, and we'll see shortly how we did that later. Let's go to the next slide. If people need to spend more time looking at this stuff, the source code's available. Take a look at it.
Yeah, and also feel free to pop in on Discord and ask any of us questions on it. We can help you out if you have any questions.
Definitely. All right. Let's actually get into the start of the program. And I use the word start as a label to say this is my starting point. It just, other people use entry, other people use other names. It doesn't matter. I like using start.
Yeah, I know some people like to use the name of the program itself as the entry point too. So if your program was called dot, you could call it dot.
Yeah, I don't like that. I don't like that.
Let's get into tabs versus spaces.
Yeah.
To be honest, I do it like Steve does too, but I have seen some other source code where the entry point is the name of the program itself.
In C, everything starts with main. Same thing with
main.
Main, M-A-I-N. That's the main is where it starts.
Mm-hmm.
There's a reason for that.
Yep. Now, when it comes to your variables and like that, in BASIC, when you define a variable, define 0. This is not the case with assembly language. The variables you're going to have to clear. And we're going to go through and start doing some initialization. The first thing we're going to do is clear the screen. We want to, this is like a p clear command. So what I do is I load up X with the screen memory location plus the screen size. And what this does is actually points X to just the 1 byte beyond all that.
And so 1 byte past the end of the screen.
Yeah, right. 1 byte past the end of the screen. The reason why is I'm going to be using the decrement X option when I'm moving along. But as you notice, the minus sign is before the X. That means it gets minused first before X get used. So when I do the clear X comma minus X, or the clear comma X minus, it will decrement first and then clear the byte.
So we had to start off one to the right because we're going to be subtracting before we begin.
Exactly.
Yeah.
And then to figure out, have I gotten to the beginning of memory and all clearing this stuff? It does a compare X with screen memory. And that's the beginning of screen memory. So if we still have not reached that location, it will loop back and clear. So this is a very tight loop that does nothing more than clear out the screen, which is 6,144 bytes. As you can see here, I'm using these labels that I set up earlier for screen size and memory, screen memory and stuff like that. That way, if I go to a larger screen, I only have to change them in one place at the beginning of the program. I don't have to change them within the program.
Right.
And also for the pointer for the screen, like he was mentioning, if you're doing page flipping, so you have two screens, say one's at 2000, one's at 3000 hex or something like that, you could actually just change screen memory to 2000 or 3000.
Exactly.
Top part of the code, and it would instantly change the rest of your program to follow.
Exactly. All right. But that one just puts zeros into the screen. It clears it. Next slide. You're there already. Good. Now, since the X register is pointing to the beginning of the screen when it finished clearing the memory, I went ahead and just stored X into this screen. It saves the start of screen there, so it knows about that. Now, there's a couple of variables I was using called dot memory and what was there. This is to help me clear the screen later, but I should probably initialize it with the information that's on the screen so that when I clear the screen, it isn't garbage. As I said, assembly doesn't set these things up for you. So I stored X into our location of our dot memory. This is where the dot was on the screen before. And then I pulled the information off the screen with the load A comma X and then stored it at what was there so I can erase it later. Something that will be self-evident when we get out into the main program.
One thing I should mention that maybe basic programmers may not be familiar with is that like BASIC tends to initialize variables for you when you first use them.
Yeah,
assembly language does not do that. Assembly language could have random stuff from a previously running program. It could have random stuff from when you first turn it on. So you have to basically assume that you have to initialize everything yourself.
Exactly. Next screen real fast. This one here goes through and sets up the video display generator for the proper graphics mode. It loads up A with that reference I made earlier about what is the information for a P mode 4 video display generator, and then stores it at the VDG port, which is FF22. So once again, this helps with these labels that make sense. They're almost self-documenting of what's going on.
Instead of you memorizing every single IO address that the Coco has.
It gets confusing. Anyways, next slide.
Okay.
Now we're going to try and keep moving quickly here. All right. This first one is setting up information and call that SAM setup routine that I had earlier, where it loads up the information about the SAM's P mode information, loads up how many bits are related to it. That's if you see the SAM V registers, BC stands for bit count. It's just a notation for me.
Okay.
And SAM V registers is the memory location for where the addresses are for V1, V2, and V3. Then you simply call the routine and it goes through and sets it up. Now you can also see by me having this routine that sets up the SAM somewhere else, when you look at this part of the code, it says, okay, this is information for setting up the SAM, and then we're moving in set SAM data. Okay, we're setting up the SAM. It helps, makes the program more understandable from when you look at it later.
Self-explanatory.
You got it.
Yeah, I guess what I'm not following here real quick, if I can just ask a quick dumb question. I understand load A and load B. That's the A and B registers. But isn't X the combination of A and B?
No,
Nope,
that's
D.
D.
D is.
Oh, that's
D.
D. Okay, that's where I got confused. Okay, never
Okay.
mind.
Yeah, very good. It's good to ask those. All right. And then we also have to tell the video display generator where in RAM should it find the video screen. And that's what this next segment does. So the load A is I'm taking the screen memory and dividing it by 512 because the way the SAM works is it can only have the video display generator or the video display memory starting every 512 bytes. So it could be at location 0, 512, 1024. You get the idea.
Mm-hmm.
Yeah. Anyways, let's go to the next one. This is more like how you have to set things up in BASIC. You've got to program your variables. Otherwise, they're just garbage if you don't. And this is basically setting up for the X and Y position. Now, remember before I said that the position is actually a 16-bit number where the first byte is the whole number of the position and the second byte is like a fractional. Well, what I'm doing here is you've got 32 is the position I want. I multiply it by 256, so that will go in the top byte. And then I add 128 to it, which is 128 divided by 256 or 0.5. So I'm basically putting 32.5 into the X position. The Y position is getting 64.5. So that's what's going on there. That's why I'm multiplying by 256 is to get that first.
Oh, so you get a rollover, so it goes to a new byte, and you're using that byte for your. Okay.
Yeah.
Gotcha.
If you remember, a byte has values.
255 is the highest, so it's 256 forces it to go over to the next byte.
Yeah. Exactly.
Okay.
Next slide. The next slide, we're talking about setting up the deltas or the speed that the ball is going to move. And the first one, low D with 100 hex. And I'm purposely throwing different ways of numbers at you. Hex makes it easy to see that 1 is going into the high byte and 00 is going into the low byte. And that means it's going to move 1 dot per game cycle or frame cycle.
And just for reference, if he was doing it the same way he did on the previous slide, he would have done load D 1 times 256 plus 0 in this case.
Right. And then we store D at delta. We load up Y with a whole number 1. And then we're moving at 0.25. That's what the 40 is. It's 0.25. So we're actually moving a little faster on the Y. And the reason why we're moving faster on the Y, you're also looking at more scan lines. You're looking at 192 up and down, where it's only 128 across. So I just decided to do that. It just makes for a more interesting display. Let's go to the next slide. Yeah. Steve's staying on top of this. I love it. Anyways, we're actually now at the main loop, the beginning of the loop that we're going to go through and do everything. This is the key. And the first thing we're going to see here is we're going to update the X position by loading D with X position, adding the X delta to it. And then we got to see, did we go off the screen? And that's the number of dots across. Now, remember, the high byte has, of the 16-bit value, has the whole number in there. So I'm taking the number of dots across, multiplying it by 256. So we're comparing against the high byte only, essentially. And did we move off the screen? Branch of lower means that we're still on the screen. So we're skipping to X in range. It means we're good. Let's go to the next slide. Well, since we are basically going to go off the screen, well, we need to basically reverse our direction. The way we do that is we basically do a negative to whatever our speed is. Easiest way to do that is get a 0 into the D register by clearing A and B, and then subtracting our delta, our X speed from it. And then
so 0 minus the current speed, which makes it negative.
Right, exactly. It takes the negative of what we got. Now, by the way, if the speed is negative, it makes it positive. You take a negative from negative. So this
in that case there, 2 wrongs make a right.
You got it. And then what we do is we add that delta back to X position. We've got them back together in the D register. And if we go to the next slide, the first instruction there is to store that new position into the X position. So we've saved that. Now we're going to do the same thing with the Y. It's exactly the same. We're going to load up into the D register the Y, go through, and let's see, check to see if we're still on the screen as far as the Y goes, and branch if we are. If not, we do the same thing with the negative. Yep. Let's see. Let's go to the next slide. We do the same thing as far as, making the Y negative, adding that new,
speed offset. Yeah.
Yep. Yeah,
and then adding
offset.
it to the existing Y position.
Sorry, and a notice came on my screen going, okay, what? And then we store it in the Y position. We're done. So we now have the new X and Y position. Well, it's now time to calculate what that new X and Y position is on the screen. So we load up A with the top half of Y position, which is the whole number.
Yeah, next slide. There you go.
All right. Yeah, on the next slide. Sorry about that, Stevie.
It's okay.
Then we load up the B register with the number of bytes per line. And then we use the multiply. So what we've done is we're trying to figure out where in screen memory is this particular position. And we've now got that.
So when you multiply, it's always A times B?
Yep.
So you don't have to specify which register?
No.
Yep.
No.
Okay.
No. There's only one multiply. It's this one. So they just made it simple. So it's multiplying A plus times B, and then it's putting the answer in D, the two of them together. And so I add this screen. Remember that variable that we put together in the direct page? That has our current screen. That's being added to the what we've calculated. So we now have the position of the beginning of the scan line that is the position for this particular dot. And then we transfer the D register into the X. So we now have an index register, which we're going to need later, pointing to that. All right, next slide. We now have to deal with the X position. And we actually kind of have to deal with the X position twice. First, we have to find the byte on that scan line that holds our dot. And then we have to figure out which one of those four positions in that byte is the dot. So we'll first grab the X position. That's the whole number on the top. Divide it by 2 twice. So we get to divide by 4, because remember there's 4 dots per byte. And the ABX, it adds whatever's in the B register to the X register. So
and then it figures out the number of bytes from the left side of that current scan line the dot is supposed to go to.
Exactly.
I was just thinking the math would have been a heck of a lot easier if we had an 8-bit wide dot that moved 1 byte at a time.
Why do you
it wouldn't be moving a dot, it'd be moving a stick.
Yeah. Well, like Stevie, if you remember, there's that 320 by 200 or 400, whatever it was, graphics mode on the PC that was 256 color.
Yeah.
That's why they liked it. They didn't have to do any masking.
The bytes just worked out.
Every byte was a single pixel, so you didn't have to worry about masking. The calculations are easy.
Yep. That's why they did. Not to give you 256 colors. It's just freaking easier. Okay. So let's go to the next slide, Stevie. All right. Now we have to deal with which particular bits within that byte do we have to deal with. So we load up B with the X position again. We AND out the bits that we need to only worry about, which are the lower 2 bits that represent from 0 to 3 for our 4 different positions. And then I multiply it by 2. And the reason why I multiply it by 2 is, remember earlier we had that data table that had masking information and color?
Mm-hmm.
Well, that was 2 bytes of information per dot. So what I do is I multiply by 2, load up the location into the Y register, And that's what the load effective address mask color data, comma, PCR does. This allows us to figure out what that location is relative to the program counter, and it puts it into the A register. And this is an instruction that Curtis is very familiar with, because this allows you to do things that are PC relative or program counter relative, which is key to OS 9.
Yeah, this is position independent code, which means if the program moves, this offset of where it's pointing to moves with it. So if I loaded the program, like Steve has this program loading at 3F00, if you wanted to move it to 7F00 because you got a 32K code to try it on, then the program just automatically all works and shifts everything over. If you hard-coded Y to point to a specific memory address, and then you had to move everything, it's now pointing to whatever random garbage was still in the old address. And the new address, who knows?
So it's just a different way. I mean, I could have said load Y #, mask color data, and it would have gotten it. But this way here, it takes about the same length of time, and it's programmer counter relative code. And that's what the PCR stands, programmer counter relative. And then we simply, remember we had built up that B register to point to an offset into that particular table. Well, Y contains the table, and the B, Y, that load effect address B, Y, adds the B to it. So we are now pointing at that location and like that. So that's basically what that's doing. We're getting very close to the end, folks, so hang in there. All right, remember before I talked about the fact that we had a dot on the screen, and well, if I didn't erase the dot, you would start having lines on the screen instead of dots, because it would just keep drawing the dots up there. Well, this first three instructions, we load up A with what was there. This was what was at the old graphics location before we had wrote the dot. We load up the U register. Curtis, don't get upset because I'm using the U register right here.
Oh, go ahead.
Yeah, it's U register is used for a lot of things in OS 9. You don't want to destroy it. But anyways, load up U with the address of where that location was that we had the graphics data, and we simply store the old data onto that memory location with the store A at U. It basically erases the old dot from the screen. All right, now we load up the A register with what was there, and before we change it around, whatever, we store it at what was there. I mean, so we load up A with what's on the graphics screen that we want to change, and we save a copy of it so we can erase it later. Simple enough. You got that, Stevie?
Yep.
Okay, next slide. Now, this here is how we mask. We simply do a AND A with the information that has to do with clearing out the bits that we're going to change, so they're 0, and then we OR in the bits of what's going to be basically the color of that dot, and then we store it in the X, store A at X, stores it on the screen. So we've only changed the dots that we wanted to that are, the bits that we want to that represent the dot, and like that. And the last thing we're doing there is restoring X at dot memory that remembers where this particular byte was changed. So this routine not only puts the dot on the screen, but remembers what was there before so it can be removed later.
So the ANDing is the masking and the ORing is the painting in.
Yes.
You got it.
Okay.
All right, let's go to the next slide. Now, if we were just simply going to go through and do this without any sort of time delays or try and sync it to the screen or anything, the dot would be moving so fast you'd probably never see it. If you do it in BASIC, you would see it, but in assembly, you won't really see it because it's going to spend a lot of time just zipping across the screen and be a blur. So what I've got here is a routine that waits roughly a 60th of a second. I'm going to use the X register count. The reason why is this number is larger than 256, which is the maximum you can count when you're using an 8-bit register. So we have to use a 16-bit register, which is the X register. I'm using this particular case. And the label, so we can have something to go back to, is called delay. And you simply say this load effect address -1, X is decrementing X by 1. It's removing 1 from X. And we're just waiting until it shows the 0 flag is being set, which is an equal instruction. But when the 0 flag is not set, it is not equal and loops back to delay and keeps looping forever.
So it's almost like a for next loop.
Yep. It's like a for next loop, and we're just waiting. We're waiting roughly about the time. The reason why I'm using the numbers that I'm using, for example, is this particular delay function of subtracting 1 from X and branching if we haven't reached 0 takes roughly 8 clock cycles. So that's the reason why we have the clocks 60 hertz divided by 8. That's roughly how many times we want to go through the loop to wait for that 60th of a second to go by.
Yep.
And believe it or not, we then branch up to the main loop and start the whole process over again of figuring out the new X position and moving the dot. And that's the program. And basically, end, start absolutely makes no sense unless you think about it this way. The word end means this is the end of the program. Don't add anything after this. We're done. The word start after the word end says this is the entry point. This is where you go to the program to start. So that's why it doesn't, when you look at it, it doesn't make sense. But when you're an assembly language wizard, it makes perfect sense to you.
Okay, and start. No more code and set the start location.
Yep, simple as that. And believe it or not, that's my effectively on the next slide is my last one. Lesson 12, we're going to look at data objects. This is going to let us move more than one object on the screen. We're going to have 3 balls bouncing around.
Neat.
Yep.
So
That's
just to
definitely-
reiterate, since I've been out for the last couple of weeks, you're using the setup that Paul Fiscarelli is using, which is
Yeah.
LW tools
Exactly.
and Notepad++.
Yep.
Yep.
Yeah, I've got the source code right now pulled up on the screen, which might make it look a little bit better than it did in the slide format. But this is what you'll be able to download from Steve's link, is the ASM file, which is the assembly language source code. And then there's also a disk file that would let you inject the program onto that disk. So it's pretty cool. And if you don't mind, Steve, what I'd like to show is just how easy it is to actually assemble this and run it in VCC based on Paul's setup.
Go ahead.
Yeah, so right now this is the source code in Notepad++, and there's the language definition that color codes the commands and the variables and the comments, right? So all your different tab stops are the different syntax components here have different colors to them, right? So visually it makes it a lot easier to see. And yeah, so I mean, it's not a huge program, but like you're saying, it's 180 some odd lines of code and pretty short program. And that includes all the various comments and everything else. So you would use Notepad to create your assembly code. In this case here, you're going to be able to download it so you don't have to type it from scratch. This is not the Rainbow magazine. So then what you would do is, and this is all, again, this is based off of Paul Fiscarelli's series, Long Branch Never, but you have your one directory that's your 6809 assembly code, and you have a program called assembbat, right? So you type in assemb. That's the assembler batch file. In this case here, we're going to type in .move, which is the assemb file. And then here we could pass it off to VCC, or I could pass it off to MAME for that matter too. So in this case here, I'll pass it off to MAME. So now the assembler's running. It's now injecting everything. Unknown support type MAME. Oh, I forgot about that. It's not MAME. It'd be like Coco 2. You don't type in MAME, whatever. I'm getting all these freaking errors popping up here. That's because I'm an idiot. I'm an idiot. Stop giving me all this freaking God.
Yeah, you got to quit out of main.
There we go. It finally went away. All right, so what is it? It's not MAME, but it'd be like Coco 2B, right? Or Coco 2. Right? Or I should have just typed in VCC. And here it is. So I'm going to move the screen over. It's still loading MAME, loading machine. Okay, so this loads up MAME. and now it's loading in the file, and it would have been faster in VCC at this point. But here it is. Here's your dot move, and now the ball is bouncing. So the moral of the story here is with this setup, you have the notepad, which is your editor. You type it in, you save your file, then you type in assem space, the name of your assembly file, and then you follow that with the emulator you want to push it out to, VCC or MAME or XROR. And the ball's bouncing. And we can see here it's bouncing smooth. It's not blinking. There's no flashing effect on here. And it is not, like Curtis was saying, it's not doing 45-degree angles, right? So it's pretty nice how it's going.
I should mention, too, this is greatly slowed down because of that time delay Steve put in. I mean, if you took that sucker out, you'd barely be able to see this thing.
Right. So if I did the same thing, and instead of typing in Coco 2, if I just typed in VCC, it would actually probably run a little bit faster, and you would get without that disk noise, too, which I still was getting from MAME, right? So here's the VCC version of the file. And then boom, boom, boom. It's just bouncing that double wide pixel. Because I've maximized it now, the aspect ratio has been distorted. It's a rectangle instead of a square, but you get the idea here. So very quickly, with the little series that Paul Fiscarelli has set up for us, we can start assembling pretty quickly. And so all future lessons that we're going to do in this series will be using Paul's environment. So good stuff. Very good stuff.
And one thing I want to mention, there's a lot to take in here because this is the first time we've been hitting like programming the SAM and the VDG and stuff, and maybe it's not totally understandable to people yet. I mean, basically this program is set up for P mode 4, so we'll just leave it at that for now and get into details later. But I think one nice thing for people that are just getting started in this, like I said, this might be a lot to take in one shot, but just fiddle with some of the variables that Steve did the starting labels on. Change the angle, change the two deltas, change the start position so when you fire up the program, the dot starts a different spot. Change the time delay so you can make it run slower or faster. You can kind of figure out how the program works doing those things and seeing what the effects are.
Mm-hmm. Exactly. And, like if I wanted to really set it up a little nicer, the mount that I was setting up for the deltas, the speed for the X and Y, I should have defined those at the beginning. That way you would just change variables at the beginning opposed to somewhere in the middle of the code if you want to change how fast the ball moved.
That sounds like an objective for the user to try.
Yep. Set up a variable called something like a init x speed or whatever, and you can put that in. But, it's basically it's just something to play around with. Now, when we get into later the series, I'm going to be talking more about the stuff that I've added to the program that's new, opposed to going through the entire program every time. So you will need to kind of realize these are going to build upon the foundation from the previous episodes.
Yeah. So we have Paul Fiscarelli giving us Hello World, where we can put text on the screen, and we have now Steve Bjork saying Hello Pong.
Yep. Eventually this will become a Pong game.
Yeah.
And next week's lesson, which we're going to talk about how to create data objects. This is more advanced versions of variables that allows you to have code that's reusable. Like if you want to have, let's say, you want to have 3 balls bouncing on the screen once, you only have to have code for 1 ball. And with the fact that you've got a data structure or a data object for each individual ball, they can run independently, and you don't have to do that much work. And I'm all for not doing that much work these days.
Spoiler alert, this is the secret of Steve Bjork's programming from the past.
Yeah, later we're going to get into how we create the how we fire up the objects and like that, and I'm going to teach you how to become your own version of a god.
Ooh.
You actually have a routine called God that spawns all the objects in your game, and that gets to be fun.
I don't think
I would just like to say I'm a little bit offended by the term God. So if we could change that to something else.
How about deity?
Deity.
Just spell it backwards, and it's okay.
If you use David Ladd, I would completely be okay with that. So.
Okay.
Bruce Moore has joined us. Bruce Moore. Paul Fiscarelli is here. Paulie Walnuts is in the house. We are all here. Hey, Bruce, I was going to take a break. Would now be a time before we start the break, maybe to start the break with the video you gave me today? Sure?
Also, oops.
Oh, it's way too late.
What if, knowing what I know now, I could go back in time, join Tandy Corporation, and change the course of history?
How does it feel?
Coco forever!
I'm still believing.
I haven't seen any of the other retro or even modern communities try to pull off something like this. This is unique.
Switcheroo, the hottest selling cocoa product of 2018.
cocoforever.gracenote.ca.
Ooh.
Stevie, before we go on too far, we did have at least one comment in chat, and it had to do with the fact that the direct page variables kept the program from being relative. And no, that's not necessarily true, especially in the case of OS9.
You mean as far as keeping it position independent?
Exactly.
Okay. So direct page does not modify the fact that it's still position independent code.
Right, exactly.
Yeah, and in OS9, if you fork a process, especially under OS9 level 1, it'll actually give each process its own unique direct page.
Excellent.
Just want to make sure they were understanding what was going on there when we were talking about relative code.
Okay. Well, I want to say thank you, Steve, for now 11 great episodes of Learning Assembly, because I'm probably not the only person who says, I wish I learned it back then. I always wanted to as a kid, and I never did. And if only, if only there was someone out there who could, teach us this thing. And luckily we have these people in our community like yourself and Paul Fiscarelli, and we have now Rick Adams' project is going to be sharing his source code with his current project, letting you be a fly on the wall to what it's like to be, develop software like a rock star. So good stuff. And so I guess this next part here, we're going to make it a multi-purpose core dump.
Right.
And is that okay with you, Nick Marentes?
Yep, no problem.
We're going to let Rick lead this thing off, but before we get started, because this is a professional show, we do have a little segment infographic here to let everybody know we're about ready to have a core dump. So get ready for this, folks. Get ready for Core Dump. Discussions, solutions, and brainstorming, hosted by Nick Marentes with special guests this week, Rick Adams. All right, so the core dump is about to begin. So how about we start? How about we start with Rick Adams? Tell us what you've got going on right now, Rick.
Well, it's really kind of timely that we were looking at a bouncing dot
earlier, because I have an assembler program that does dots moving around that I've been working on. Basically, this is the very, very bare beginnings of what I'm hoping will be Temple of Rom version 2. And I'm starting it very slowly and very methodically. And I've got no timetable. I can do it as slow as I want. And just for fun, I'm opening up the process so that anybody can watch me as I develop this. So all my source is on GitHub, and so you can go out there and get it, and you can, get in on the ground floor, and it's barely doing anything right now. So it's moving dots around, but it's not. It doesn't look like anything like what Steve had. So let me turn this around and show you. Here's what my program is doing right now. So
dots are moving from left to right across the screen.
Right.
And you're also masking out the background or foreground, depending on what we're looking at here.
Yep. So what this is I have just now, the latest thing I've added to the program is that it does double buffering. So there are two screens in memory at once, and it's drawing on one screen while it's displaying the other screen. And then right at the critical trace interval, which is when it's just starting to paint the screen, it flips, and the screen that was just painted gets displayed, and then I clear and paint on the other screen. So they just sort of flip back and forth.
Look at that smooth animation.
Super smooth.
It's very smooth.
It's like butter.
But it's very slow. And so what this shows me is that the design of this program is naive. Because I assumed that it's like, I've got a 6309. I'm doing it in 6309 native mode. So I'm gonna get about a 10% speed boost. Hot dog. I am loaded for bear. But the cocoa giveth and the cocoa taketh away. I've got a larger, a more, cool resolution than I had before.
Yeah.
So it's more memory. And as a matter of fact, the last problem that I had to solve was the fact that you can't fit two screens in memory because it's just too big. There's not enough room in memory at any one time in your 64K map for two screens and your program. So I had to, use the memory management unit, the MMU, and and use that to map in, one screen and then the other. So I'm not real good at the MMU. I figured out just enough to get it to work for like Shanghai, but I didn't really understand how it worked. And now I understand a lot better. But so at this point, I need to restructure this program. And I mean, I could think about a less high resolution, which would be, less screen size and faster to process. I've got to figure out, what goes in the interrupt routine and all kinds of things like that.
What resolution are we looking at now? Is this the 320 or the 640?
Yeah, it's the 320 by 225.
Oh, okay.
And 16 colors. Because I wanted to use a 16 color mode. I'm tired of 4 colors.
Sure.
I wanted a little bit more. So
obviously this is Coco 3 only.
Yeah, exactly.
35 years later.
I got a question for you, Rick.
Sure.
The way that you're erasing the dots off the screen, is that by copying the entire screen back in?
Yeah. So basically for each, it's very naive, as I said. So for each frame, I erase the entire screen, and then I draw it all from scratch, including
yeah, that explains a lot.
Oh, yeah. So it's not doing draw, redraw at all. So
right. Well, based on that, then that's,
And literally each screen is almost 36K. So, I mean, that'll tell you how much memory it's moving around.
Well, Rick, you've seen my Z89, right? Game?
G89.
Yeah,
Oh,
that's
is that like the Zaxxon thing?
that's a Zaxxon for the Coco 3.
Right. Sure.
Now, on that game there, when you play it, not only did I use instead of the 320 dot across mode, I used the 256 dot across mode, but I
Sure.
also windowed it. I made it smaller because I
Ooh,
constantly had to redraw the screen because we're scrolling at
Yep.
that weird angle. And that was required. That's just the way you have to do it. There's no way to do a 320 by 200 screen and redraw the thing every game frame. You're going to be
Right.
looking at about 12 frames per second at best.
Right.
Yeah, that's even
So
with
the
a
goal-
609.
So the goal at the end of the line here, if I can make this work, which is debatable, is to do a temple of ROM that does sprites instead of vertical and horizontal lines. You know, and it's a little bit fancier than the old version.
Yeah.
And so I've got a long way to go here.
Well, the question is, how
Well-
many sprites and how big are they going to be on the final game?
Right. Well, the sprites are going to cover the entire screen, but the sprites aren't going to be, the sprites are going to be at least 50% black. So there is that.
Right.
Now, the one thing that I just did, somebody was suggesting that I wasn't doing a stack blast for the clearing of the screen that I'm doing, and I've tested the clear the screen routine. I set the border to red at the beginning and set it to black at the end to see how much of the 60th of a second am I taking up with the clear routine. And the answer is all of it and then some.
Yep.
So
yep.
I redid the clearing the screen routine, and so that is over here. And to make it a little bit more efficient, and let's see if it'll ever stop being blurry. It will not. It's not going to be.
That's
all
fine.
really.
It's copy protection. So.
Yeah.
It's encrypted. That's what it is.
Yeah, it's macro vision. So.
Well,
So
that's
anyway,
the thing. Well, one of the things I was going to suggest is you're going to have to look at it. And there's two ways of doing it. You can do a complete screen blast to erase all your graphics and put the base screen back up there and put the new graphics on top of that. Or you can do something that's basically save a copy of what was underneath the sprite. And then what you do is you just erase that back in. Now, that's what I did on Rampage. So you just had the gorillas moving around. Basically, the way the game worked as far as doing the graphics, if there was changes to the buildings, I did those. Then I did the sprites on top of it. And even though I had pretty big characters in Rampage, I was still able to get a pretty good frame rate out of it. But it was not, it basically when I drew the graphics up at the same time, I was making a copy of what was on the screen, similar to what I did in the program where I had what was there, for the dot. I saved that, put the dot up, and when I went to erase it, I transferred it back on. It's something very similar to that, but it's a list, and you build up the list one way, and then you run backwards, and that erases the information off the screen.
So it's sort of like a combination of, double buffering and raw redraw.
You got it.
Yeah, so that makes sense. Bomb Threat uses draw redraw. It's just one screen, and I just draw things as you go, and there is a little bit of a flicker. So okay, so it's going to be So obviously, the idea that you can clear the screen for each frame and redraw everything completely from scratch is naive. So. Well,
I wouldn't say naive. It's a way that's done on most systems. It's just the Coco is so slow compared to them.
Yeah.
I mean, the 609 will help in some spots in that, but there's also like design considerations to do too. Like right now, you have the entire screen being viewed as the game itself. On the actual final product, you'll probably have a section at the bottom for score and number of men left and everything else that you don't have to redraw every single frame. So you'll save some time there because you'll only be updating that, as the score changes or the number of men changes. So.
Well,
You
that's the
can
thing.
time
With
that.
Z89 did exactly that. It had your score, your fuel, and all these other gauges and information up there. So it made the window even smaller that you had to
Right.
refresh every time.
Yeah, so there's little tricks like that you can do. You can put a board around like Steve did on Super Pitfall, and I might have done on Zach's C89 as well.
And
You
then
know,
on
tricks.
and then this is just sort of a proof of concept that I'm doing, and it isn't really. It's like the line drawing is completely naive. It's like it's like for
It's
I
brute
equals
force by
1 to
dot.
300. It's brute force by dot, exactly. It's PSET. So, and if you were doing that for real, you would have a vertical line routine and a horizontal line routine that would be optimized for drawing that kind of a line.
Yeah, we
And
did that
it
in
wouldn't
Nitrous
be-
9, and holy cow, did that make a big speed difference. Like multiples of speed, not just like
Which is
1.5.
Which is what the original Temple of Rom did. So that's why everything is vertical and horizontal lines. I knew how to do diagonal lines, but it took too much time, so I couldn't do it.
So are you planning on the game still being kind of vector art for the temple itself, or are you going to be a little bit more embellished than just the outline of the temple?
I was thinking that it was going to be completely, filled in sprites, and now it looks like, well, that's probably not going to be possible.
Well,
So it's gonna happen.
when I hear the word sprite, I'm thinking of the foreground character. But you're talking about for the background, would that be more like tiles, like tile based?
Tiles, yes. Okay,
Yeah.
that's the buzzword I'm looking for. Yeah.
So tile based, and you're going to do hardware scrolling too?
I'm gonna try. I think it seems like if you're going to be scrolling around, in all dimensions like Temple of Rom did, which was kind of its tour de force. If you could do that with hardware scrolling, that would be really nice. Now, I don't really know enough about that yet to be able to do that, so it'll be interesting to learn that.
Yeah, that's something I'd like to tap into one day too. I'm way not ready for that part yet, but no, that's cool.
How are you copying the screens?
I'm not copying at all. I'm just completely clearing the entire screen and redrawing it from scratch every frame.
How are you clearing the screen?
With a stack blast.
Or TFM if you're a 6 or a 9, if I remember correctly.
I did try that. I did that, and that worked. But now I'm doing a stack blast. I've heard that it is faster than TFM.
Yeah, if you're just doing a clear, a stack blast is even on the 609 is a little bit faster than using a TFM. But if you're copying screen data, then a TFM is faster than any stack blast can be.
Right. Okay, that makes sense.
And one other trick I wanted to mention that like King's Quest 3 and some of the Sierra games use is that it's actually drawing a 320 mode screen, but it's treating it like a 160, exactly like Steve did with his bouncing ball, where he's treating it as a 4-color screen when it's really a 2-color mode. Because then you can take all the masking of having to do the foreground and merging pixels with the background stuff, and you can just trash all that because everything's a single byte. Like we were mentioning before, VGA, like 256 colors, what's 1 byte per pixel. Well, you're just doing 2 pixels at a time. You treat them as a double pixel, and then you don't have to worry about all the masking stuff. You're just drawing raw bytes at a time.
Right.
You get your virtual res will be 160. It'll look like the 160 mode, but all the calculations are much simpler.
DEFCON 2.
So I would imagine a lot of discussions on Discord will be taking place as you continue to hammer this through, right? So
Right.
Yeah.
Yeah, there's just so many different ways of doing it. It's trying to find which way works for the type of game you're doing or a program. It's just trying to figure it out in the end.
Right. But you know what I love about it, Rick, is there's many things I love about this. Number one, you're sharing it.
Yeah.
Number two, even though you have done things in the past, you're doing new things. You're entering uncharted territory, and so you're basically not bashful about enlisting help from the community. And I just think that's a testament to both your lack of ego as well as the community all coming together, just wanting to brainstorm and help you, make this. So it's it's very awesome.
And that's the thing. And that's the thing. I'm going for maximum fun. It's like you can have fun, or you could make money, or you could do some combination of the two. And for this one, I'm going for maximum fun. So, and I did this stuff a long time ago, and then I wasn't doing it for a long time, and now I'm getting back into it again. So I pick it up pretty fast because I did it so long ago. But I don't know everything yet, and I'm okay with that. So I don't care that people are watching me struggle.
Sure.
Yeah, well, it becomes a group learning project rather than you just
Yeah.
trying to learn this stuff. Everybody gets to learn from it. I'm sure I'll discover new things that I haven't tried before either. So,
Right. I'm really kind of hoping to lure people in because I've barely started. People that it's like, can I do assembly? Or I'm just starting to do assembly. How does one do this stuff? If I can lure people in to look over my shoulders and watch me do it and learn along the way, that would be awesome.
Well, you're doing it already. This is great.
Yeah, that's it.
Well,
So
I think it's a lot of fun, and I like more people to have fun. So
It's like the wizard showing what's behind the curtain.
Right. Yep.
while sewing the curtain.
While gnawing on the curtain.
yeah.
I'm really disappointed at how slow those dots are. I'm really surprised. But then I look at my program and it's like, okay, I got I got subroutines calling subroutines calling subroutines, and I got one dot at a time and all kinds of stuff. It's like I thought I had all the time in the world to draw this frame, but no, that's not true.
No. That's the thing about the Coco 3 is that you jump from that 6K screen to a 36K screen. You just start to realize how hard it is to push that memory around.
Yeah, I mean, you've doubled your CPU speed, but you've increased your screen size by 600%. So,
yeah,
let's do
That's
that.
a net loss.
It's a factor of 5. You really have gone 5 times more memory to move around. So you're
Right.
actually going 2.5 times slower.
So it is a little bit tempting to go for a less elite resolution. That would solve a lot of problems, but I don't know if I have to do that yet. I love this resolution. I may or may not be able to keep it.
Well, there's other tricks too. I mean, like one of the advantages I even used to use this in BASIC for the extended or for the Coco 3 is that there's tricks you can do in the Coco 3 you can't do in a Coco 1 too. So if you want to animate flames or something, just shift palette registers around type thing, which takes almost no time at all. Whereas on a straight bitmap, you'd have to be redrawing these flames or water or whatever it is every time. So there's other tricks you can do to speed it up or give the apparent increase in speed.
And only change the things you need. Don't change everything.
Yeah.
Right. The victory screen in Shanghai did that with the palette animation. Yeah.
Or the waterfall demo that we've seen, reposted
Right. Yeah.
recently.
So
And you may
it
not
really isn't-
need. Sorry.
Go ahead,
it
Nick.
isn't really- it
You
isn't
may
really
not
worth my
need. You may not need to copy and everything of the whole screen.
Right.
Like
Exactly.
Curtis said earlier, I mean, you devote part of the screen to be your static areas like the score display. That'll shrink the size of the screen, so then you straight away got less memory to play with. So there's a speed up without reducing the resolution of the overall game.
Right.
Mm-hmm.
Well, what you really need, Rick, is scores where the digits are yay tall, where they're taking up about 3/4 of the screen, and that really cuts down the amount of graphics you have to.
Yeah,
Scoreboard
it'll be exactly
for the
like playing Doom or Castle Wolfenstein on a 286 where you have the little postage side stamp thing because that's the only thing I can handle.
Yeah. So at this point, for me to optimize this thing this proof of concept that I have to make these little dots move faster would involve a lot of work optimizing code that I'm going to throw away down the line. So at this point, I need to go for drawing sprites and drawing them as fast as I can and starting to put sprites on the screen. And then after that, I can work on scrolling them in all directions.
Yeah.
So,
I mean, you've seen
can-
Thexter, which I mean, it runs under OS 9 even faster than the original cartridge version did, and that's scrolling almost the entire screen, but it's using little speed up tricks like we've been discussing. So, and it doesn't run at too bad of a frame rate.
Mm-hmm.
Yeah, that'd be kind of cool. Even if you're pulling off a Thexter look for Temple of Rom would be actually very cool.
Uh-huh. So I have a question, which is, so obviously it looks like the clearing the entire screen takes more than a 60th of a second. So is that always going to be true? It's just always going to take maybe about, three screen cycles?
Well, you're killing 36,000 bytes. If you're using a TFM, that's 3 cycles per byte. So we're whatever the math is, and that's over 108,000, I think, CPU cycles. If you use stack blasting, I'd have to figure out, it depends on how many registers you're pushing on the stack and then how long your compares take to figure out when you're done your stack blast. Are you doing the full width of the screen so you can just keep zipping along without having to change it? Or are you doing a central part where you have to like stop after the line's done and then skip it up to the next line? And there's a lot of variables you got to figure out in that first.
Yeah. Well, one of the tricks I used when I was developing the games is, I'd always try and go the fastest frame rate, but some games I couldn't go faster than every third frame I would switch, and then I would lock it down to that speed. So every game cycle was 3 frames. So that's what I would do, is start thinking about what you can get it down to and then lock it to that speed. That way you're not going to have the thing speeding up and slowing down, which is the most annoying thing to a game player.
Yeah.
Correct.
You'll make Stevie never get past level 0.
You'll make him DEF CON quick, but
I'm good with title screens and game over screens.
And to be honest, I mean, for the Coco, I don't know if 60 hertz should be the holy grail anyway. I mean, we were dealing with NTSC, which is only doing every odd line, every second refresh. You're really doing only 30 frames per second to begin with anyway. People have watched movies for 100 years that are only running at 24 frames per second. So it isn't that critical to get it going quite that fast. So maybe just don't worry about it.
Yeah, my goal is always to do something closer to 30 frames per second anyways. It's just, I know how much work it's going to involve, so I just do it that way.
Yeah, and quite a few games did pretty well with other even divisions like 15 and 20. I don't think I'd go probably below 15 for an arcade game, but 15 or 20 actually doesn't look that bad either.
It'd just be nice to know the scale that I'm dealing with. It's like clearing the screen is going to take N screen cycles. It's like, what is the value of N? I don't know. So,
well, the one example you're using, 320 by 225, using the 639 TFM command, it's 108,000 cycles. Stack bus would be a little bit faster depending how many registers you're pushing at once. And then you take, there's 1,780,000 cycles in a Coco 3 running at full double speed, divided by that amount. That tells you how many frames you take, or you can generate per second, just clearing the screen, not drawing anything else on top of it, not doing sound, not doing gameplay.
Yeah.
But yeah.
My brain can't do that calculation right now.
Well, it looks cool so far. We're looking forward to seeing more. We will watch your career with great interest.
Do you use the 320 by 200? Like, does the game require it?
It would be nice. I mean, the original game. Yeah, the original game was almost full screen. So.
But you can do full screen, but choose a lower resolution. You can pick a resolution that's half the size.
Right.
And still be full screen as such,
Yeah, like you're doing with yours and on Gunstar.
Exactly. I mean, I have the same problem. I can't do a full 36K screen, so I went for one that's half the resolution effectively, but the pixels are automatically double sized.
So I may have to go for a lower resolution.
But keep the color resolution, because to be honest, the color makes more of a difference visually, I think, than the number of pixels.
I really want 16 colors instead of 4. I really have to insist on that. So I may or may not be, I may be backing off on this resolution. That makes me a little bit sad, but we'll see.
No, you just have to make a viewport that doesn't use the whole screen. Like
right.
Yeah, or not worry about 60 frames per second, worry about 20.
Right.
If that runs smooth. Like how fast did Temple of Rom run? I don't think it was 60 frames per second, was it?
I have no idea. I just put it together and it worked. I didn't measure anything.
Can we poach you on that?
Well, that's the thing is, maybe for now, don't worry too much about what's going on. Let's get the stuff up on the screen, what you've got, and then we back off, take a look at, is it better to clear the entire screen first and start over, or is it better to restore the screen?
Right.
Because you may only be transferring 1,000 bytes every game cycle to restore the screen, opposed to transferring 36,000.
Right. Yeah. See, what I'm doing now in this proof of concept really isn't relevant for what I'm going to be doing for the project. Because the project is really all about drawing things and then scrolling it like crazy. So that's a completely different problem. So I need to start working on that problem as opposed to this one.
Yeah, I mean, depending on the size of the map, I mean, if you make the game 512K, you could literally have the entire map in memory completely rendered already. You just blast that, just do a copy. You're not clearing anything. And then just blast it on and then overprint your sprites and restore, as Steve said, because you have the entire map already expanded out graphically in memory, and you just restore from those points wherever you're redrawing underneath the sprite.
Right.
And there are some techniques depending on if you're trying to scroll horizontally or vertically. You can do it in hardware scrolling too, where you only have to build the part of the screen that's coming in, opposed to rebuilding the entire screen. So there's a lot of techniques. I mean, Marty's Nightmare, I just scrolled up and down on that game and didn't really worry about drawing that much stuff.
So I don't know hardly anything about hardware scrolling right now, which is great. This is an opportunity for me to learn. So
Yep.
We just got now. The thing is, you can't do hardware scrolling where it's a simultaneously left and up. Let's say you can go horizontally, you can go vertically, but not both of them at the same time.
Well, you can to a limited extent. You have to enable that 256 byte mode, but that means you only get, like in a 320 16 color mode, you're only going to get about a screen and a half width that you can scroll back and forth on. You can go vertically right through all of RAM, but
Right, exactly. That's the problem. It's just if you're going to be scrolling, let's say 2 or 3 screens to the left, you can't do 2 and 3 screens also to the right. I mean, to above.
Yeah. Now, on the other hand, if you drop the res, say you did a 160 mode, like, you know, Predator or RoboCop did, well, then it's still a 256 byte wide mode. You can actually get about 2.5 screens. I don't know if that's enough for what you're doing or not, but that might be an option.
So I want 16 colors. That's a big thing. And then the other thing that I would really like, and this is another area where I don't know enough yet to do this, but I know it can be done. I would like to have a more continuous sound, possibly interrupt driven.
Definitely. If you want it continuous, it'll be interrupt driven, trust me.
Yeah. Temple of Rum had this really wimpy sound that I just hated. It wasn't what I had in mind. You know, I had in mind when you fire that laser, I wanted to hear, you know, and you just got this little when I was developing it, my kids were playing it, and in this room in my house, and I was coming up to the house, and I looked through the window, and I could see them playing it, and they're firing the laser, and I just had this idea in my head that it's like, yeah, that looks like, that looks great. And then I walked in the house, and then I heard the actual sound. It was like, and it's like, and I'm like, oh, that is so pathetic.
Both Nick and Steve can help you with that because they've done a lot of background IRQ driven sound routines. And
well, not only that, there's all these new options of sound chips now for the Coco. I mean, we can have some stuff that's killer ass.
Can you say
Simon
that?
Jonathan too. He's got some code ready to go. So
So so this is all. It's some areas where that's new to me, and I get to learn it, and possibly I can drag some people along with me, and they can learn it too. And I don't have to pretend to know everything. So it's all good.
Yep, there you go.
I really like the fact it's a group project, a group learning project where everybody gets to learn along with you.
Now, I've got it on my GitHub, but the GitHub has like a long, unpronounceable name, and I need to change that to something simple like Rick Adams. Right now, it's the GitHub of Yggdrasil Radio. And it's like, well, good luck, spelling that. That's the name of my online radio station. So we'll fix that to something simpler.
Cool. Well, it's from humble beginnings, right?
Yes.
Very cool. Well, I'm very excited to see another Rick Adams. Yeah. I'm very excited to see another Rick Adams project out there taking shape.
Of course, now I got to finish OmniStar.
Of course, did we leave enough time for Nick?
Yeah, we got time for Nick.
Oh, I'm sorry. Yeah, I don't want to take all the time.
Yeah, no, I wasn't sure if Danny was just asking the question. That's all.
We got lots of time.
we got all the time in the world, and this is
Well,
only the first of 9 shows we're going to do today. So
Only 2 hours.
Yeah.
All day long.
So for anyone who wants to follow this, Discord's probably the best place at this point. Rick has got links to where to find the source code on GitHub with the unpronounceable name.
I just posted it in the YouTube
Right.
chat.
Okay, and there's also been an ongoing discussion already on some of this stuff too. So feel free to join in or just follow along if you want to learn this kind of stuff yourself.
Mm-hmm.
absolutely, yeah. Cool. Well, we will look forward to more and more updates on this, and whenever you want to show us something new on the show, you've got an open forum to do that. So look forward to those updates. So we've had so many things premiere on this show, like Bomb Threat, that your project from a year ago now. It's hard to believe it's been a year since Bomb Threat. And now, actually, I don't know if we've done an actual official premiere of OmniStar yet, but we'll probably due for that in the near future, right? So, yeah, lots of premieres. So when we're ready to give sneak peeks and premieres, we'll do it. We'll do it live.
Rockstar Pilot debuted here too. So.
Hey, Steve.
Yeah.
When you see the latest version of OmniStar, there's sort of some surprises. And so if you play it, you're going to see those surprises, and it's going to spoil the game. So I wonder. Well, I mean, I suppose I could turn that feature off, and you could do a demo of it. But when you see the latest version, you'll see what I'm talking about.
Okay. We'll have to take a look at that. This concludes another episode of Coco Talk, the world's leading live talk show featuring the Tandy Color Computer. For all things Coco Talk, visit us on the web at cocotalk.live. We'd love to hear from you. Send feedback, suggestions, even segments via email to cocotalk@cocotalk.live.
Coco Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Coco Talk is rocking the 8-bit world.
Consider supporting the show with a purchase of merchandise from our retro swag shop at 8bit256.com. If you'd like to become a patron of the show, click the Patreon link at our website at cocotalk.live.
Coco Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Coco Talk is rocking the 8-bit world.
Coco Talk would not exist without the community, its cast, crew, and contributors. Thanks go to Curtis Boyle, David Ladd, Mark Overholzer, Grant Leedy, Bruce Moore, Nick Marentes, Ron Delvaux, Rick Adams, Jason Reichert, Richard Lorbieski, Jim Brain, Tom C., Rob Inman, Mark Bosley, Brian Joyce, Ken Reichert, David O'Connor, Brian Weasler, Terry Steggy, Nick Marotta, John Strong, and many more, especially to Steve Bjork for production suggestions and James Differendaffer for making my head explode. Please help support the Coco community by visiting some of its various contributors. A list of resources is available at imacoconut.com. That's imacoconut.com. The Coco Talk theme song is copyright 2008 by D. Bruce Moore and Greg Sheeler. Mixed, mastered, and produced by D. Bruce Moore.